Hello children, today we will start our discussion from heading Stereochemical aspects of Sn1 and Sn2 mechanism for optically active halides. So as you know that in Sn2 mechanism a transition state is formed as an intermediate state, and this transition state finally converted or decomposed in the form of product and byproduct. Okay, so the product which is formed here is having inverted configuration. Okay children, inverted configuration, and so the formation reaction of the product under Sn2 mechanism will be known as inversion. Okay children, and in the case of Sn1 mechanism, this Sn1 mechanism is taking place in two steps, and in first step carbonium ion is formed, which is a trigonal planar structure with central carbon atom sp2 hybridized. Okay children, and that is why finally under this mechanism Sn1 mechanism, a racemic mixture is formed of two optically active forms of the product. Okay, dextrorotatory and levorotatory. So this dextro and levorotatory product forms are present in 50:50 ratio, and that is why this mixture will be optically inactive and will be known as racemic mixture, and formation of this racemic mixture is known as racemization. Okay children, the next we are moving to next heading, relative reactivity of haloalkanes towards Sn1 and Sn2 reactions. Okay, so in Sn2 mechanism, this alpha carbon is that carbon of the alkyl halide with which halide atom is attached. So alpha carbon with halogen atom is having repulsion for the incoming nucleophile from the direction in which this already nucleophile is present. Okay children, so incoming nucleophile attacks on this alpha site from back side. Okay, now if the valencies atoms or groups which are present with this carbon atom are comparatively having high electron density or a bulky nature, then the incoming nucleophile which is going to attack from backward direction will feel steric hindrance. Okay children, so crowding at the alpha site due to the presence of bulky groups here, which makes this nucleophile, this attack of this nucleophile impossible here, is known as steric hindrance. Okay children, so as you can see here, in the case of primary alkyl halide, this is the carbon site, alpha carbon site, and this nucleophile is going to attack from back side. It is not possible for it to attack from this side because nucleophile is already present in this side, and that is why this nucleophile will repel to a next incoming nucleophile. Okay, so nucleophile will attack from back side, and if this alkyl halide is primary in nature, so all three valencies of this carbon will be satisfied with hydrogen. These hydrogens are having comparatively smaller electron cloud, or you can say these are comparatively less bulky groups. So this nucleophile can attack from this backward side easily. But as far as this hydrogen will be displaced by alkyl group, so the related alkyl group will have comparatively larger electron cloud, and that is why the attack of this nucleophile in this condition will become little bit more harder in comparison to here. Okay children, so in primary it is comparatively harder than methyl halide, and secondary more harder, and in tertiary it is going hardest one, because 3 alkyl groups are present with very big electron cloud. So repulsion will be there between among these alkyl groups. Okay, and this repulsion, due to this repulsion, the attack of this nucleophile will become hardest here. Okay, and this hardest condition due to the presence of these bulky groups here is known as steric hindrance. Okay, so due to the steric hindrance, this nucleophile will not able to attack on this carbon site here. Okay children, so you can say that tertiary alkyl halides will be least reactive for Sn2 mechanism, whereas primary or methyl halide will be most reactive, and opposite will be in the case of Sn1 mechanism. Okay, because in Sn1 mechanism carbonium ion is formed as intermediate, so tertiary carbonium ion will be most stable, and that is why reactivity of tertiary alkyl halide will be most or highest. Okay, so the reactivity order of alkyl halides in Sn1 mechanism will be opposite of that in Sn2 mechanism. Okay children, the next page, a difference between Sn1 and Sn2 mechanism is given here in this page. So you can sum up these differences. The first point, in Sn1 mechanism these follows first order kinetics, because that is rate of reaction depends on the one concentration term only. Okay, and that is why these are represented as Sn1 reactions. Okay, Sn1 reactions, whereas Sn2 reactions follow second order kinetics or second order mechanism. Then second point, tertiary halides generally follow Sn1 mechanism. Okay, but in Sn2 condition primary halides follow Sn2 mechanism. Third point, for the same halogen atom the order of the reactivity from tertiary to methyl halide, and for Sn2 reaction it is opposite of Sn1 from methyl halide to tertiary halide. Then fourth point, the rate of Sn1 reaction is influenced by electronic factors, whereas steric hindrance has no role. Okay, but here in Sn2 mechanism, because this whole conversion is taking place in one step, so steric hindrance is also playing a very important role here in Sn2 mechanism. Then fifth point, polar solvents favors Sn1 reactions. Polar solvent means aqueous solvents. Okay, non-polar solvents means alcoholic solvents will favor Sn2 reactions. Then sixth point, in case of optically active compounds racemization occurs in Sn1 mechanism, and in Sn2 mechanism inversion occurs. Okay, then last point, reaction proceed in two steps in Sn1 mechanism, and intermediate is carbonium ion, and here in Sn2 this mechanism is one step mechanism, and here transition state is formed, which is a highly energetic, and that is why very less stable state, transition state. Okay children, the next heading is reactions of alkyl halides, and here we are going to discuss some very important nucleophilic substitution reactions. Okay, so as I told you already that in nucleophilic substitution reaction comparatively more active nucleophile displaces less active nucleophile from the alkyl halide. Okay, and product is formed. So first, replacement by OH group. So in this first substitution reaction, halogen atom of the alkyl halide will be displaced by OH. So overall you can say alcohol will form. So for this, alkyl halides are reacted with aqueous KOH or moist silver oxide, and this moist silver oxide will be Ag2O plus H2O. Okay, and the product which will be formed here, alcohols. So example is given here. Ethyl bromide is reacting with aqueous KOH forming ethanol. Okay children, and same way methyl iodide is reacting with moist silver oxide. So moist silver oxide will form silver hydroxide, and this silver hydroxide will react with alkyl halide. So methyl iodide with moist silver oxide will form methanol plus silver iodide. Okay, the next is replacement by alkoxy group. Alkoxy group OR. So oxygen and alkyl group, collectively known as alkoxy group. And in this reaction, halide ion or halogen atom is displaced by alkoxy group. Okay, so ether will form as a final product. So this formation or this displacement reaction of halide ion with OR is known as Williamson synthesis, and this is a very important reaction for the synthesis of ether. Okay, so when alkyl halide is treated with sodium or potassium alkoxide, ether is obtained. Okay children, so as you can see here in this example, ethyl bromide is reacting with sodium ethoxide and formation of diethyl ether is taking place. Diethyl ether. Okay, next formation reaction is also given. Ethers can also obtained by heating an alkyl halide with dry silver oxide. This dry silver oxide. So here we require 2 molecules of ethyl halide. When this will react with silver oxide, diethyl ether will form with AgBr as a byproduct. Okay children, so what is the difference in these two reactions for the formation of ether? So under this first reaction, Williamson synthesis, we can form both symmetrical and unsymmetrical ethers, or you can say symmetrical or simple or mixed ether. Okay, so simple ethers are the ethers in which both the alkyl group which are attached with oxygen are same, and mixed ether are the ethers in which these alkyl groups are different. Okay children, so for formation of mixed ether, we have to select appropriate sodium alkoxide here. Okay, so if any alkyl halide is given already, and then we will select appropriate halide, sodium alkoxide, and this selection of sodium alkoxide will be depend upon that which ether we are going to form. Okay, and when related alkoxide will react with alkyl halide, related mixed ether will be formed. Okay children, and one more thing that you have to keep in your mind, that you are not going to use this alkyl halide as a tertiary halide when you want to form any such mixed ether which is having a tertiary group. Okay, so in that condition you will use tertiary alkoxide, sodium alkoxide you will use in tertiary form, and this will be tried to always in a primary compound only. Okay, if you will use tertiary alkyl halide, then your main product which will be formed here will be alkene. Okay, Detail of this reaction we will discuss in ether chapter. Okay children, so main point I have told you already here, and by this reaction we can form only simple ethers, okay, which are having same alkyl group. So this is the difference between these two preparation reaction of ether. The next reaction is replacement by cyano group. So in this reaction halogen atom will be replaced by Cn group, okay, and for this we are using alcoholic potassium cyanide as a reagent, and this alcoholic potassium cyanide will form cyanide ion as a nucleophile, and this nucleophile will displace this bromide ion, okay, then related alkyl cyanide will form. So for example, ethyl iodide when reacting with potassium cyanide alcoholic, then ethyl cyanide or propane nitrile is formed, okay. So suffix which is used for Cn is nitrile. We will start numbering from this side, 1 2 3. So propane and suffix is nitrile, propane nitrile, okay children. Then this Cn is here acting as a nucleophile, and this Cn is a type of ambident nucleophile, okay children, ambident nucleophile. So what are ambident nucleophiles? Such nucleophiles which are having more than one attacking site, but at once attack from one site is taking place, okay. Such nucleophile which are having more than one attacking site, but at once they are using their one site only for the attack, such nucleophiles are known as ambident nucleophiles. As Cn group, NO2 can behave as NO2 and ONO, okay. So in this case the nitrogen will be attacking site, and in this case this oxygen will be attacking site, okay. So two sites can be used as attacking site, but at once one site will be used, okay. So when attachment will be through nitrogen, then nitro compound will form, and when attachment with through oxygen, then nitrite will be formed. And same case here for Cn group also. When alkyl group attaches itself from carbon, then alkyl cyanide will form, and when alkyl group is attaches itself from nitrogen, then isocyanide will form, okay children. So ambident nucleophiles, very important term. So how Cn is going to attack on this carbon site, the explanation is given here. Potassium cyanide is an ionic compound, and it gives this cyanide ion, okay. So in this condition both carbon and nitrogen are having a lone pair of electron, and that is why this can attack from both the side, but CC bond is stronger in nature than Cn bond, and that is why attack from carbon site is taking place to this carbon site, okay. So overall ethyl cyanide will form. Very little amount of ethyl isocyanide will also form, okay children. Next is hydrolysis. So in this reaction under this heading, what we are going to discuss, what is the use of alkyl cyanide, okay. How can we use in different conversion to this alkyl cyanide, or you can say this cyano group, okay. So if hydrolysis is taking place, then cyano group of alkyl cyanide is get converted in the form of amide group or in the form of acidic group, okay children, in the form of amide group or in the form of acidic group. So when partial hydrolysis is there, partial hydrolysis, then amide will form, and when complete hydrolysis is there under same condition, then related acid will form. Okay children, so these are very important conversion you have to keep in your mind. So from alkyl halide you can form alkyl cyanide, and then you can form related amide or acid. Okay, one more thing we can do with CN group, it's reduction. Okay, it's reduction. So when we reduce CN group, here you can see, when we reduce CN group, then reduction can be done in two different conditions, and accordingly the related compound will form. So under partial reduction condition, this reduction is also known as Stephan reduction. Okay, so under Stephan reduction, first imines are formed, related imine hydrogen chloride, means imine salts are formed, and these imine salts on hydrolysis get converted in the form of related aldehyde. Okay, related aldehyde. So this reduction, partial reduction, and it is known as Stephan reduction or Stephan reaction. Okay, so first imine hydrogen chloride will form, and this imine hydrogen chloride, when hydrolyzed, aldehyde will form. Okay, then we can do complete reduction of cyno group, and this complete reduction is known as Mendes reaction. And under this reaction, when related alkyl cyanide is reduced with hydrogen in the presence of nickel as catalyst, then primary amine is formed. Okay children, so here this nitrile is having just one carbon, but here you can see that this amine is having two carbon in chain. Okay, so increasement in the carbon in chain, ascending in carbon series. Okay, the next is formation of isocyanates. So when alkyl halide is reacted with silver cyanide alcoholic, then major product will be alkyl isocyanide. For example, ethyl bromide with AgCN alcoholic is forming ethyl isocyanide. Okay, explanation is given here, and this explanation can be asked to you under reasoning. So silver cyanide is a covalent compound, and that is why only an atom has electron pair for bond formation here. Okay, so this site will attack to the carbon site of the base compound, and that is why alkyl isocyanide will form finally. Okay, now how can we use this alkyl cyanide in different conversions? So first is hydrolysis. So alkyl isocyanide can be hydrolyzed to primary amine. Okay children, primary amine, and always formic acid will form as a byproduct. Okay children, formic acid always will be a byproduct form, okay, with related primary amine. For example, when methyl isocyanide is hydrolyzed, then we will get methylamine plus formic acid. Then second is reduction. So we can reduce alkyl isocyanide, and under reduction condition, in the presence of sodium and ethanol, secondary amines will form. Okay, so under Mendes reduction, alkyl cyanide are forming primary amines and isocyanide are forming secondary amines. Okay, so methyl secondary amine will form. Methyl secondary amine. Okay, this carbon of isocyanide group will be converted in the form of methyl group always. Okay, so isocyanide will form related secondary amine. For example, ethyl isocyanide will form this secondary amine, and the name of this secondary amine is ethyl methyl amine, or you can say N-methyl ethanamine. The next is reaction with ammonia, and this reaction is also known as Hofmann ammonolysis. Hofmann ammonolysis. Okay children, so in this reaction, alkyl halides heated with alcoholic ammonia in a sealed tube, and then mixture of all types of amines plus their quaternary salt is obtained. So this overall conversion is known as Hofmann's ammonolysis. A very important, very popular, very common reaction, Hofmann's ammonolysis. So alcoholic ammonia with ethyl chloride is forming ethyl amine with HCl as a byproduct. Now this ethyl amine, which is a primary amine, when reacted with next molecule of ethyl chloride, then a related secondary amine, diethylamine, is formed with the same byproduct. And when this secondary amine is again reacted with ethyl chloride, tertiary amine is formed. And tertiary amine with again ethyl chloride is forming quaternary salt. Quaternary salt, tetraethyl ammonium chloride. Okay children, so this whole conversion is known as Hofmann's ammonolysis. So as you can see, all the type of amines with their quaternary salt is formed here. Okay, so overall we are getting a mixture of different amines and quaternary salt here. The next is replacement by nitro group. Very important reaction, replacement by nitro group. So for replacement of halogen atom by nitro group, we use potassium nitrite as a reagent. Okay, so potassium nitrite will produce ONO group. ONO means nitride group. Oxygen will attack on this carbon site and ethyl nitrite will form. Okay, as you can see here, ethyl nitrite will form. And after that, this heading ambident nucleophiles is given. This I have clarified you already. So we are moving to next page. These are the reactions, few reactions. Okay, so these are not in your syllabus, so we are not going to discuss these all. Then next type of reactions which are given here, the 11th one, formation of higher alkynes, and this reaction is going to very important for you, different type of conversion. So here you can see that when haloalkanes are treated with sodium alkylide, okay, you can say sodium salt of alkynes, okay, sodium alkynides. So related alkynes are formed. Related alkynes are formed. Okay children, and these alkynes can be converted in a related alkene by reduction or related alkane by further reduction. Okay, so this reaction is very important for different type of conversions. Okay children, so ethyl, for example, which is given here, if you want to convert ethyl group which is having 2 carbon in a chain of 4 carbon, so we have to take sodium acetylide. Okay, now if you want to convert this 2 carbon chain in 5 carbon chain at last, so what you will take? You will take sodium salt of propine, sodium salt of propine. Okay children, So when you will use this propyne here, then you will get at last chain of 5 carbon, okay, or alkyne of 5 carbon. So accordingly we will adjust this sodium salt of alkyne, which will be depend upon how much carbon we require in our resultant alkyne. Okay children, so if you require 4 carbon atoms finally, then you will use sodium acetylide, or if you require 5 carbon atom, then you will use sodium salt of propyne accordingly. Okay children, the next heading is reduction, very important. So for the reduction of alkyl halide, as you can see, we can use number of reagents. Okay, and most common reagent are metals with hydrogen. So hydrogen with alkyl halide in the presence of most common reducing metal nickel, you will get alkane. Okay, so alkyl halides under reduction conditions are always forming a related alkane. Okay children, so you can use any one of reagent which is given here. Okay, so these are the some common reactions, substitution reactions with reduction reactions of alkyl halides. So you just go through with the same pages which are given in your book and try to write different examples which are based on these reactions. And if you are having any problem, you face any problem, you can share your problem in your class group. Thank you very much.